Okay, so let me introduce our first speaker for the today's sessions, morning session of the researcher meet. Hello. I'm saying. Uh, our speaker's name is Maitri Pathak. She is working with Dr. Ajay Nath, and she is from the Institute of Information Technology, Vadodara. And her today she will be talking over formation of the matter wave droplet lattices in multicolor periodic confinements. So, Maitri Pathak, stage is yours. You can start.
Okay, good morning, everyone. First of all, I would like to thank the organizer for inviting me at Quantum Information and Quantum Technology 2023 conference. So the title of my presentation is Formation of Matter Wave Droplet Lattice in Multicolor Periodic Confinement. This is the joint work with Dr. Ajay Nath at Indian Institute of Information Technology, Vadodara. So I will start with the introduction. Of quantum droplet, which is the topic of my work. So we know that the droplet are being reported in nuclear physics, where the nucleus behaves like a fluid and it forms a spherical droplet-like profile, and then there is an interaction taking place like strong nuclear and Coulomb interaction. So interaction is an important part, it plays an important role to realize a droplet. In liquids, we know that there is a van der Waals force which is acting. So there are short range and long range interaction taking place, which result into the self-bound state of droplet. Now, on quantum level, recently new type of quantum fluid after liquid helium is being reported, which is quantum droplet in ultra cold atoms. Realizing this quantum droplet at ultra cold atom is interesting because the interatomic interatomic distance is very much larger. So it cannot signify this van der Waals interaction. Thus, there is the origin of this quantum droplet is not the van der Waals interaction, whereas it is the quantum fluctuation, and this quantum fluctuation are result of the 0-point energy associated with the atom in the ground state of Bose-Einstein condensation. Now, in 2015, this quantum droplet were first reported by D.S. Petro, where he put forward that when in BEC mixture or in Bose mixture, there is an interaction which is repulsive. It is having a feature like gas. So BEC is, we can say it as a quantum gas also. When the interaction are repulsive and when there is an interaction are attractive, the system was getting collapsed. Now, D.S. Petro, he considered two species of bosons, and he realized that when mean field and beyond mean field is a LHY correction. So when this mean field and beyond mean field are basically competing with each other. So this collapse is being stabilized when mean field and beyond mean field become comparable to each other. And this LHY term is basically coming from the quantum fluctuation in the at the ground state of BEC. So when this both the interaction are comparable to each other, we report a quantum droplet profile, which is the signature feature of quantum droplet is basically the flat top profile. So the system which he took was Bose-Bose mixture, mean field and beyond mean field interaction, and in free space he realized quantum droplet. So as he went on increasing the atom number, the droplet feature was significant. So it was in 2015 when this new quantum fluid was put forward. Now we are trying to study this quantum droplet in multicolor optical lattice. Now the motivation of study of quantum droplet in multicolor optical lattices, solitary waves are also being reported in 4-color optical lattices. Quantum droplet are numerically studied, and their stationary and dynamic properties are studied in one-dimensional optical lattices. Phenomena like Anderson localization and negative temperature are also being reported in optical lattice potential. Thus, it is a very rich test bed to study the novel phenomena like Anderson localization and negative temperature. Now, the brief algorithm which we have considered in our work is, we have started with a two-component Gauss-Pitov-Whiskey equation. Then we have scaled it to a single component Gauss-Pitov-Whiskey equation. Then we have considered an NSAT solution. Then we have moved from single component Gauss-Pitov-Whiskey equation to a solvable differential equation. And in between, we have got a set of consistency condition. This consistency condition are very much important because they gives the form of potential, mean field and beyond mean field interaction, and the phase part, and the form of wave function also. From this wave function and potential, we can analyze our system. So by plotting the density of quantum droplet from under the influence of this multicolor optical lattice, we can study them. Now, the system which we have considered in our work is one-dimensional BEC. We have binary BEC. We have considered multicolor periodic confinement and beyond mean field and mean field interaction. We have considered this two-component Gauss-Pitov-Whiskey equation, where this is the kinetic energy term, this is the mean field term, and this is the beyond mean field term. Psi1 and Psi2 are the associated wave function to the binary mixture which we have considered. These are our scaling parameters. Then with the help of the scaling parameters, we have reduced our two-component Gauss-Pitov-Whiskey equation to a single component Gauss-Pitov-Whiskey equation. Now, over here, the potential we have considered is a multicolor optical lattice. So this is a 4-color optical lattice, and this is an exponentially periodic trap which we have considered. So combining all this, we are able to get multicolor optical lattice. By changing this G1 from J equals to 1 to 4, we are able to get optical lattice, bichromatic optical lattice, 3-color optical lattice, and 4-color optical lattice. This is the form of our LSAT solution. Further, we got this set of consistency condition while moving towards solvable differential equation. By solving this consistency condition, we are able to get the non-linearity G1 and G2, which is G1 and G2, which is mean field and beyond mean field and mean field interaction. The phase part and the amplitude part of our wave function can also be obtained from this generic form. V1, V2 and V3 are the amplitude part of our potential which we have obtained. Now the traveling coordinate to obtain the multicolor optical lattice is of this form, from which by substituting this in our consistency condition which we have obtained, we are able to obtain the amplitude part of our wave function, phase, mean field and beyond mean field interaction. And this is the exact analytical form of our wave, of our potential and wave function. So P1 and P2 are basically the tuning parameters in our case. Now, this is the generic form of our potential. So we have analyzed our trap and we have found that by changing the P1 and P2, which we can tune by tuning the power of our laser experimentally. By tuning P1 and P2, we are able to generate various traps such as free space, optical lattice, bichromatic optical lattice, 3-color optical lattice, and 4-color optical lattice. So this variety of potential are being generated from this potential. Now over here, we have plotted the geometry of our potential, where we have tuned this P1 and P2 in our potential form, and by keeping P2, P1 changing from -5 to 5. So this is basically the triple well super optical lattice, and this is the double well super optical lattice which we are obtaining by tuning P1 and P2. from the above potential, we are able to generate from in this plot. We have shown the number of potential which we are able to generate. So over here, we are in figure C. We have plotted that we can obtain symmetric and anti-symmetric optical lattice, bichromatic optical lattice, three color super optical super lattice, and frustrated double well super lattice, and over here lattice potential, and then over here biperiodic frustrated super optical lattice. So these are the potentials, these are the confinements we are able to obtain from the potential of this form. Now, considering the two-color optical lattice, so in two-color optical lattice, this is the form of our potential where we have changed our P1 value and kept our P2 equals to 0, with the help of which we are able to get a two-color bichromatic optical lattice. And we see that in potential, when we are moving from free space to optical lattice, we are moving towards a droplet profile, droplet profile where the superposition of our potential geometry is being superposed on the density profile, and we can see a periodic pattern over here. So we can see that as we are increasing the depth of our potential, we can see that there is the more and more superposition of the droplet potential is being done on our potential, on our droplet. And one important thing which is there is the droplet profile, which is the Fred trough profile, is still significant. So this fragmentation is taking place on our quantum droplet, but the flat trough profile is still present in our system. So the reason is that over here we are to study this reason why the flat trough profile is still present in the system where we are giving an optical lattice is because the mean field, when we are plotting mean field and beyond mean field interaction, this is the expression of our mean field and beyond mean field interaction. So when we are plotting that, we observe that from 0 to minus 1.5, which is this value, the mean field and beyond mean field interaction are comparable to each other, which is the signature feature to realize quantum droplet. So this is an reason why the flat trough profile is still present on further increasing the potential depth. Similarly, now we have taken the positive value of P1, whereas in the previous case we have taken negative values. Over here, when we are changing our potential from V equals to, so from free space to biperiodic optical lattice, we report that the localization is taking place, and we are further moving towards a solitonic nature. And the flat trough profile, it is not present in our system. Now this localization is signature feature of a disordered system, and bichromatic optical lattice is a disordered system. So this localization is a phenomena which is reported before also for bichromatic optical lattice. But when we are varying this P1 value, we are moving towards a localization. Now, the reason why the flat trough profile is not reported for this case is that when we are changing our P1 from 0 to 1.5, from 0 to 1.5, our mean field and beyond mean field are not comparable with each other. Because of that, the flat trough profile is not present in our system. Now, similarly for 4-color optical lattice, where our P1 and P2 both are not equals to 0, both are having some values. So we will obtain a 4-color optical lattice, which will give a double well super lattice density pattern on quantum droplet. So when we are moving from optical lattice to a double well super lattice potential, we can see that the feature of the potential is superimposed on our quantum droplet. And similarly, for 2-color optical lattice, we were having a flat trough profile. Similarly, over here also, when we are changing P2 from 0 to minus 1.5, we are having a flat top profile. For that, we again analyzed our mean field and mean field beyond mean field interaction. And we saw that for P2 equals to 0 to minus 1.5, we have basically mean field and beyond mean field are again comparable to each other. This is the reason why flat top profile is present in our system, whereas we are increasing the depth of our potential. Further, for positive value of P2 from 0 to 1.25, we are basically having, again, we are reporting as localization is being reported, and the geometry of our potential is being superimposed on our quantum droplet, and localization is being reported, and the peaks are getting reduced, thus which is the feature of a disordered system. So for that also we saw that for P2 from 0 to 1.5, our mean field and beyond mean field were not comparable to each other. So thus we are not able to realize the flat top profile, which is the signature feature of quantum droplet. So these are the, so for 2-color optical lattice, which is shown in figure A, and this is for the 4-color optical lattice, we have plotted mean field and beyond mean field interaction. And the analysis is coming out to be same for P2 to minus 1.5, and for P1 equals to 0 to minus 1.25. The mean field are comparable, thus we have reported a fragmentation, but still quantum droplet feature is present. And further, mean field and beyond mean field are not comparable to each other. So there is no quantum droplet feature present in the system, and localization is taking place. Now we have checked the stability of our solution by doing Bogoliubov-Digen's equation. We have calculated the gain, and further we have plotted the gain, and we have found the instability region, and we have found our solution to be stable by VK criterion also. So the conclusion of our work is we have basically solved a one-dimensional extended GP equation for a multicolor optical lattice, and from which from this multicolor optical lattice we are able to obtain symmetric and antisymmetric optical lattice, bichromatic optical lattice, 3-color optical lattice, and 4-color optical lattice, depending upon the suitable choice of our solution. Thus, on quantum droplet, we have reported the density pattern of periodic and biperiodic form by tuning the trap parameter, and the phenomena of Anderson-like localization and fragmentation of quantum droplet are studied in 2-color and 4-color optical lattice. Then to study the phenomena of Anderson-like localization and to analyze the phenomena of Anderson-like localization and fragmentation in our system, we have plotted the profile of our mean field and beyond mean field, and which are comparable to each other for fragmentation part, where the quantum droplet feature is present, and for the Anderson-like localization, where beyond mean field and mean field are not comparable to each other, we report an Anderson-like localization. And further, the stability is being analyzed by VK criterion and by Bogoliubov-Digen's equation. So these are the references which I have used, and thank you for listening to me.
Thank you, Maitri Pathak. Now session is open for the Q&A. So anyone have the questions can ask.
Thank you for your talk. I have 2 questions. Could you please explain what is the practical use of droplet, quantum droplet?
Sir, the practical use of quantum droplet is, as the system is very dilute, so we can expect that the practical application might be in interferometry for sensor making and all those purpose. But realizing a quantum droplet in system like BEC, like quantum gas, is itself a fundamental study, like to do it further, carry on further on. So I find on the application basis, interferometry might be one this application.
Because when you say droplet, I have association with the water molecules or a liquid crystal. So, okay. Second question is, you have considered 1D nonlinear Schrödinger equation or Gross-Pitayevsky equation.
Yes.
So, do you have plans to consider 2D or 3D?
Yes, sir. For 2D, we are thinking about that, but analytically it is difficult. But we are trying to do it numerically, because analytically it will be a long, tedious process. So this is an analytical model for 1D system. So for 2D system, we need to switch to numerical methods.
Because in 1D case, nonlinear Schrödinger equation is stable. I mean, the profile of the soliton does not spread over time. But in case of 2D, it is not stable. So in your case, it is very interesting to know what will happen.
Yes, sir.
So, thank you.
Audible? Am I audible, Maitri?
Yeah, sir. Yes, you are
See, see, 2D case, two-dimensional case, it has been investigated recently. You can see we have a physical review, a paper recently, last year. So under certain conditions, there is stability. And in 3D experimental also, they have seen, in quasi 3D kind of scenario, it is stable. Now,
Yes.
one more thing. So that one, more or less should be investigated numerically. Now, one more thing is that, for example, have you investigated other phases apart from, for example, the super solid phase? The super solid is periodic, and you have a periodic lattice. We have some work on super solid phase. You can check it out, Journal of Physics. Myself and Mithilesh and others, because it has its own periodicity, and you are also putting a periodic potential. It could be interesting to see the behavior of super solid phase.
Yes.
Okay.
Yes, I will look.
Yeah.
Thank you. So, thank you for the suggestion.
If anybody have any other question, we still have time. Till then, we can check with our other speaker, Hari Krishnan. You can check your audio and video. Thank you, Maitri.
Thank you.
Hari Krishnan, are you there? Hello, Hari Krishnan. We cannot hear you. No, you are not audible. You can try to log in again, log out and log in. Hello, hello. No, you are not audible.
Hello.
Hello. Yes, you're
Yeah.
now audible.
Now
You can
audible?
check. Yes, yeah. You can check your video also.
Yes, yes.
Okay,
Yeah.
it's fine. Now,
I will just,
share your screen.
yeah, I will check. So is this visible now? Hello?
Yes. Okay. Yes, it's full screen.
Yeah.
Okay.
Okay, okay.
Okay. Then try me. Okay, there is still time. Okay, let me introduce you.
Is it starting now? Are we starting?
Okay, we can start now.
Yeah, yeah, okay. Is the other one, if the other talk is over, we can start.
Time. Okay, it's already 10:30. Okay, let me. So, should I start?
Yeah, yeah, we can, you can start. We can start.
Okay, so our next speaker is Mr. Hari Krishnan. He is from the Indian Institute of Technology, Palakkad, and he will be talking about today localizing genuine multi-party entanglement in noisy stabilizer states. So, Hari Krishnan, you can full screen your slides and you can start with your
Yeah.
talk.
Okay. Thank you. Thank you for the introduction. I hope the screen is now in full screen.
Yes, yes.
Okay, okay. Thank you. So first of all, I thank the coordinators for inviting me for this event and to showcase my work in this conference. So let me start then. I'll be talking about localizing entanglement, mainly generally multi-party entanglement in stabilized states which undergo decoherence. So this will be the outline of my talk. I will begin with the introduction to localizable entanglement. What is localizable entanglement? Then I will talk what is actually meant by localizing entanglement in noisy stabilized states. Then I will just show you the demonstrations that we did on toric code, which is one of these kind of stabilized state. Then I will summarize the talk. Okay, so we will just then start with the mandatory slides like what is entanglement. So we all know what is entanglement, even though I'm just giving you the brief introduction. So if we have a biparty state like psi 12, maybe you can imagine it as a two spin half particles. Then if the state cannot be written as a product state, then we call it an entangled state. And the kind of entanglement is a bipartite entanglement. It's entanglement between two parties. Now, if the entanglement is not only between two parties, if we have more than two parties, say, for example, three parties, for example, three spin half particles, then it's not only bipartite entanglement. We actually have different layers of different kinds of entanglement. So the first case will be, for example, shown here, the fully separable state where there is no entanglement between any of the parties. We have three spin half particles, all are in maybe 0, 0, 0 kind of tensor product states. This kind of state we call fully separable state. The other kind of state is known as the biseparable state, where, for example, you have a 0 tensor product with the Bell state, something like that. So that in the first partition, 1 is to 2, 3, it is not entangled. Whereas in the other partition, like 2 is to 1, 3 and 3 is to 1, 2, it is entangled. So these kind of states are called biseparable entanglement. These states are entangled, but not fully entangled, fully kind of entangled. But the other, if you have more than one parties, multi-party states, then the most kind of like these are the kind of states we can see. For example, the GSC state where all the qubits or all the spin half particles may be entangled with everything else. So if all parties are entangled with every other parties, so that there is no you cannot separate the state in any of the partitions, then it's called a generally multi-party entangled state or not a biseparable state. So we, in this talk, in this work, we will be mainly focusing on this kind of entanglement, generally multi-party kind of entanglement. And these are all in the case of pure state. When we discuss about decoherence, we actually have mixed state. So this is how we extend this to the case of mixed state. If you have a convex mixture of fully separable states of this form, then it's called a fully separable mixed state. And if you have a convex mixture of biseparable state, it's called a fully separable biseparable mixed state. Or if it is not biseparable, if you cannot write it as a like this, then it's called a generally multi-party entangled state in the mixed state scenario. Okay, that's the introduction for entanglement. Now, localizable entanglement. What is localizable entanglement and why we need that? Are the first is. So the scenario is that we have a system, for example, like this omega is maybe S and S prime. It's a combined system. So in scenarios where we are not interested in the total entanglement of the entire system, maybe we should be we might be interested in the entanglement within a subsystem like S, not in S prime. In that scenario, the first choice will be like just trace out this S prime and get the reduced local density matrix in S. Then calculate some entanglement measure like whatever negativity or something. If it is a pure state, we can calculate entropy or something like that. Then that will be a first choice. But the problem with this kind of thing is that this will not always work. For example, you take this GME state of GSC state, which is a generally multi-party entangled state. If you trace out one of this qubit, you actually get the mixed state of this form in the next two qubits. So that is a diagonal density matrix in the computational basis, so that there is no entanglement you cannot quantify within this state. So, but that does not mean the state is not entangled. So even you can see here that every qubit is entangled to everything else, but we are not getting, after tracing out, we are not getting that entanglement. So the problem is with the choice we are using to quantify this entanglement. So in this case of scenario, we have to look for some other quantity called a localizable entanglement. So the is formally given the average amount of on subsystem qubit project measurement. S prime we measure instead of partial tracing, we measure in single qubit project measurements. There will be outcomes k. That outcomes we are forget as in the case of partial trace. According to every
Sorry, your voice is breaking.
the reduced density matrix in the subsystem whatever there, then this quantity can be called the single qubit projective measurement your possibilities. For example, you in a single qubit phi, there are infinitely many possibilities. So you can not to get the actual value of localizable measurements in S prime as well, single qubit projective measurements. So this quantity maximum of over all possible measurements, this average entanglement is called the localizable entanglement. So here JC, as you know, it's a stabilizer state. This is not only the property of JC state, but any stabilizer state you take, you can find similar problem of becoming the state diagonal. In all these cases, you have to adopt localizable entanglement instead of partial trace in scenarios where you are interested in such a entanglement within a subsystem. So that's why we study localizable entanglement. Now, for example, JC, you take the example of JC. Instead of partial tracing, if I measure this in X basis, there are two outcomes possible, either +1 or -1. Corresponding to every outcome, you can localize the bell state in other two qubits, 2 and 3, as shown here. Now, if you calculate entanglement here, here I am using negativity. You can use entropy as well. You will get the maximum value, and you can actually see the average entanglement is maximum. Whereas if we partial trace, we get that there is no entanglement. In localizable entanglement, we actually get the actual value. So that's why we are interested in localizable entanglement in stabilizer states. Now I am formally introducing to graph states and stabilizer states. So stabilizer states, GAC is a typical example for a stabilizer state. There are plenty of other examples, those who do quantum error correction protocols, and these have many applications in error correction. So these are the state stabilized by some set of generators. Stabilized, they are called stabilizers. So I actually denote this by the get S. Now there is something more called graph state. So what is a graph state? We have a graph. A graph is a set of vertices where every two vertex you can connect with an edge. So there are set of vertices and set of edges. So this kind of graph is called a simple connected graph if there is no isolated edge. So every graph you can actually associate with the graph state, a quantum state, by this protocol. So we start with the plus state in every qubit, and we simply apply a control Z operation between every qubit which is connected by an edge. So by this protocol, you can actually get this graph state corresponding to every graph. So it can be shown that every connected graph, simple connected graph, is a generally multi-party entangled state, so that every qubit is entangled to everything else. Now it is also shown that for every stabilizer state, other than the graph state is also a special case of stabilizer state. There are many other stabilizer states. For example, the GHC is local unitary connected to some graph state. So you can always find out a graph which is local unitary connected to some stabilizer state. So that since we know that the local unitaries cannot change the entanglement within the state, this S and G will have the same entanglement. So if you want to study the entanglement in S, you can basically study the entanglement G. So that's why we choose graph-based protocol studies methodology to study this localizable entanglement. So here I have shown the graph state corresponding to GHC. It's called a star graph. There will be a central hub and all the nodal qubits. So n qubit will be like n qubits here. So that is called a GHC stabilizer state and associated graph. Now we ask the question whether it is possible to localize entanglement in stabilizer state by some protocol. So people have already shown that if there is only if we have a simple connected graph and we want to localize entanglement between only two qubits, for example, these two qubits in this case, then it is possible to do that by doing this protocol. You consider a path connecting these two qubits in the graph. Then you can measure all the qubits coming in the path in the X basis and everything else in the Z basis. So this will definitely give you a Bell state, and showing that every qubit you can every two qubit you can localize to a Bell state, so that you can simply show that every simple connected graph is a generally multi-party entangled state. So the question is that one more thing is that people have even shown that even the noisy scenario, when the graph is undergoing arbitrary noisy channels like quantum poly channels, it is
sorry,
even possible.
could you please press hide on your screen, because I am not able to see the references.
Okay. So
hide.
So it is the can I go to
no, just press there is two options. Yes, now it's visible. Thank you.
Okay, fine. Sorry. Yeah, so if we do this in the noisy scenario as well, this is possible to localize entanglement between any two arbitrary qubits. People have shown that. Now the question we are asking, whether it is possible to do this for any arbitrary graph with arbitrary number of qubits, and also this S is not only 2 qubits, but any number of qubits. So is it possible to localize entanglement within arbitrary patch of subsystem of qubits in an arbitrary graph? That's a question we asked. So the answer is yes. So this slide basically encompasses the whole point I have to make in this talk. So this is the protocol we are proposing. The idea is that now we are taking some arbitrary graph. This can be associated to some stabilizer state by some local unitary operations. We simply forget about the local unitaries and now only look at the graph. So we have this graph and we have to localize entanglement within the subsystem S by projective measurements in S prime, single qubit projective measurements. So for this moment involved in the definition of localizable entanglement. So if you do the optimization, you actually end up with the poly basis. So, but it's not yet proven to best of my knowledge, but you can easily see that numerical studies will show you that poly basis is the optimal basis. So we only look at poly basis. So here we are looking, for example, sigma 1 is an X basis, sigma 2 X Y basis, sigma 3 is a Z basis, like that. So I have an arbitrary graph. I have to localize entanglement here by this measurement setup. So how to do that? The first step to do is the every X measurement. So this is my this is our protocol what we are proposing. The X measurement, every X and Y measurement, we convert into Z measurement. So you can see there is a white. Now it was actually red. Now I made it white. So that means there is something. There is a Hadamard operation here. So that if you do the whole operation again, it remains the same. So a sigma Z measurement going through a Hadamard again turns out to an X measurement, so that everything is the same. So I'm just changing the representation. The sigma Z, I make the measurement sigma Z by applying some unitary on the graph. Now here actually there is something, it's a Y to Z conversion. So there is a Hadamard plus a phase gate sitting here. So that we denote with the diamond, white diamond. Now the third step is a non-trivial part where actually we propose something called a reduced graph construction. Actually, this methodology already exists. This measurement transformations in this you can find it in this reference. So there is a reduced graph construction. This is a iterative process. You keep changing the graph connectivities and the attributes. This white and this kind of colors. This denote basically some local operation in the graph. This will keep changing such that you at the end you will arrive at a particular graph structure that has certain properties. That property I will just spell out. The number one is that there should not be any Y measurements in the reduced graph. Now, if you look at here, we actually had a Y measurement here. Here also it is a Y measurement. But here, if you look, it's actually sigma C acting on a red qubit. So red means everything in red actually commutes with the sigma Z measurement. So even if there is a diamond kind of frame, this is still a C measurement. So that Y measurement now gone. That's a one point. The other point is that there should not be no two qubits connected in an X measurement. So we have an X measured qubit here. There should not be another qubit which is also measured in X qubit. They are connected. So that should not happen. And also the last part is that S1 prime should have only sigma Z measurement. So S1 prime is basically the nearest, the first neighborhood of the patch we are looking. We are looking at S. The immediate neighborhood is, we call it S1 prime, and the everything beyond that is S2 prime. So S1 prime should only have sigma Z measurement. So if we arrive at such a configuration, we tell that it's a reduced graph. Now we can simply perform the sigma Z measurement. So on a graph, if you perform a sigma Z measurement, that basically kind of detach this node from everything else. So now if you perform the S1 prime complete sigma Z measurement, that simply detaches S from S2 prime, and that will give you the localized graph in S. So the whole, this reduction process is the crux of this protocol. And that depends on these three iterative protocols. Now, given an arbitrary graph, this is only a simple graph with 8 qubits. We can take any number of qubits, any number of measurements. Is it possible? We ask this question: how complex is this process, the graph reduction process? So the entire localization process is basically a polynomial task. That is the one thing we saw. So we given theoretical upper bound for this complexity, how much operations. So C denotes the number of graph operations. For example, this, if you want to delete this edge or create an edge like that, and if you want to change this attribute from white to red, something like that, all these we count as a graph operation. So all these operation, if you add, that only adds up to a polynomial in the system size. Here M will be the roughly the number of qubits, or it's actually the number of measured qubits. So if many qubits are measured, it will be the order of the size. It only scales polynomial in the system size. So we also demonstrated this with some cluster states of cubic, square, and linear structures as shown. It's always upper bound is always here. Now the non-trivial part from here, all this protocol we are suggesting, this holds even if the state is initially mixture. I mean, it's a noisy state, noisy. If we try to do this, if we try to create some graph state in lab, there can be several kind of noises creeping into the system that takes into some mixed state. So even if you start from a state, mixed state that have this kind of, so we consider here only poly channels, that can be represented in this cross operator representations. So given that your graph is a mixture of this arising due to this poly channel can have Markovian as well as non-Markovian kind of nature. So here you can see there are two parameters, epsilon and q. So q is basically the noise strength. Q equal to 0 means it's the pure state. Q equal to 1 is a maximal decohertz state, and epsilon gives you the non-Markovian D parameter. So epsilon equal to 0 is a Markovian case, and non-zero epsilon is a non-Markovian case. So that we can tune also. Any graph state under any this kind of maps, for example, bit flip, phase flip, this kind of will be the special case of these things, depolarization as well. You can do the mapping, and we use this property that if a graph undergoes a decoherence under poly channel, it will be a graph diagonal state. So every graph is associated with the graph basis. So in this basis, the mixed state will be diagonal in that basis. So with this probabilities P gamma as we denote here. So we start with such a state here instead of a pure state. Even then this whole protocol goes through and you can get a mixed state in the mixed localized state in S, so that in that state you can actually study whether state is entangled or not. So we can actually give you the state form, what will be the state only in terms of the graph connectivities and etc. So that's the whole protocol. Now I'm just showing you the demonstrations. We actually did this for cluster states, linear, cubic, and ladder structures. Also, we did for the, we, as I said, that it is applicable to stabilizer state. We are demonstrating it on the toric code. It's also called Kitev code, actually put forward by Alexei Kitev in the case of topological quantum error correcting codes. So I'm not going to the system discussion because due to the time constraint. So basically, you can think of it as a square lattice. It's depend on a square lattice, and it will have stabilizers and as the plackets and vertex operators. Now, as I said, every stabilizer is associated with a graph state. This is the associated graph with this toric code. Even though it looks little clumsy, you can actually find out the exact graph for any number of plackets. So you can actually scale it. So what we do here is that we take this graph. From this graph, we actually try to localize entanglement in these non-trivial loops. So these are non-trivial loops are important in the error correcting. These are actually the logical operators in the error correcting paradigm. So we actually localize entanglement in this non-trivial loop, and we are able to show that in the noiseless scenario, this will be always a GHZ state, n-qubit GHZ state. And even the noisy in the noiseless scenario, in the noisy scenario, it will be a simply a graph GHZ diagonal state, so that we can actually study the entanglement in the system even in analytical. So the left plot actually shows you the variation of this entanglement along this non-trivial loop, which is quantified by the quantity called generally multi-party concurrence, which is actually defined for GHZ diagonal state. You can find out in the reference I will give you. We actually study the variation of entanglement with noise strength and also for the different Markovian parameters. And also we study some other this is for the bit flip noise, and for other noise also we study. And this analytical bound you can give you for in this case of toric code. This entanglement along this non-trivial loop will be given by this value EB loop. So NP will be the number of plackets. So it actually kind of scales exponentially in the system size. It will be always less than 1, bounded with 1. So that's analytical we give you. Now I am summarizing. So we actually propose a generic protocol for the localization for the entanglement, stabilized states, purely based on graph manipulations. We also show that the overall graph operations is only polynomial in the system size. And we extended the protocol for the noisy scenario, where the stabilized states can in general be decohered with arbitrary poly noise channels, uncorrelated poly non-Markovian poly channels. And also we demonstrated the protocol with Toricot and also cluster state, which we have not shown here. You can actually find the full description in this reference. So with that, I am concluding. So just glimpse into our group. This is our supervisor, and we are from IT Palakkad. And thank you for your attention.
So if anyone has some questions, please ask.
Thank you for your talk. I have a few questions.
Yeah.
So, first one is, could you please explain the concept of localization?
Yeah. Okay.
Because I have association like when localization is a wave packet. So in your case, what is?
So here actually we are localizing entanglement. So we have a whole system. We, for example, you may have seen this, like we study this nearest neighbor concurrence or something like that in the spin system. We can study if there is a like nearest neighbor interaction, we can get the reduced density matrix and study the entanglement there. And people do this kind of study to analyze quantum phase transitions, etc. So we can have cases where we are not interested in the global entanglement content of the system, but only in the local, in some local system. Okay, so in that case, maybe we can use partial traces rest of the system and get the reduced density matrix and do the entanglement calculation there. But this will not always work. So in that, where this fails, you actually have to do this kind of localizing. So what we do is basically you do some local operation here, local projective measurements, single qubit projective measurements, such that it does not on an average increase the entanglement content. So it will only localize the entanglement to some subsystem. Okay, so that quantity we call by the name localizable entanglement. So this single qubit projective measurement we take here, it can be in arbitrary, you can actually parameterize this with theta and phi for single qubits. So it can actually take infinitely many possibilities. We actually have to maximize it among all possible measurements, but we here only consider poly. Poly will anyway give you a lower bound compared to the actual quantity. So we actually perform measurements to localize some entanglement within some part of this whole system.
So,
that can be a rough idea.
So you are doing the trace to find out a subsystem and a partial trace to find out subsystem, and then doing some local operations to localize.
No. We don't do partial trace. We first do projective measurements, single qubit rank 1 projective measurements here, S prime. So there will be, for example, if there are n qubits in the S prime, there will be 2 raised to n choices, right? Computational basis, if I say. So that will correspond to k. For every k, there will be some outcome. So for every outcome, we perform the projection. So once I project, every qubit here is in a product state. There is no entanglement within S prime, and within S prime and S within that also. So we can simply trace out S prime after every projective measurement. Then that will give you some reduced state corresponding to given outcome. That will I denote with rho k here.
So what is the benefit of localization here?
Yeah, so this is the first benefit. If there are instances when you can, if you simply trace out, you will simply get there is no entanglement. For example, the GHC state, if you trace out 1 qubit, you will get that there is no entanglement between 2 and 3. But actually that is not the case. All 3 qubits are entangled to everything else. So if you want to get that entanglement, you have to perform some other operation rather than simple partial trace. You have to do the localizable calculation, localizable entanglement.
Thank you. Next question, how to identify whether I have graph state, cluster state, or stabilizer states? Are there any parameters which I need to compute to identify type of state?
Which type of state?
Yeah, you were talking about graph
Yeah.
states, so
Yes,
stabilizer
yes.
states, cluster states. So
Mhm.
is there any parameter which I need to calculate to identify whether state is
So
graph?
graph states have this particular form.
Okay.
So I think, are you asking like if I'm doing some experiment in lab, like creating some state, random state, whether I
No,
can identify it as a graph, something like that?
usually I work with a density matrix. So
Mhm.
density matrix, in your case, I see pure state. So
Hmm.
if I have density matrix, so how do I need to identify whether my state is graph state or stabilizer state and so on? So this
Yeah,
is
I
my
think
question.
you can do this here. Every graph will be, you can actually represent the density matrix with generators. So there will be n generators corresponding to n qubit graph. You can actually measure this n qubit to construct the state. I think the state tomography you can do with the measuring the generators. So then you can construct the density matrix. I think that can be a way. I'm not sure.
Mhm.
Graph state have this particular form. It's not a kind of very generic state. It's a very particular state. And
Yes,
stabilizer
but it's
state, always you can find out the graph state. They are such that they are connected with the local unitary. The line alignment will be the same.
mhm. Okay. Thank you.
Yeah. Okay, thank you.
Any more questions?
I have one question.
Yeah.
See, are you aware about the Saurabh Das and Saurabh?
Sudadan.
Huh?
Saurabh Sudadan.
So, there was a talk almost dealing with similar kind of behavior, here from ISO Kolkata. Are you aware about
Oh,
that?
actually, no, no, no. It is over.
See, he has already, I think that paper is there in the archive.
Yeah.
Saurabh Das
Mhm.
and one of our students here. You can
Okay.
check it. Archive is there. I think it has been
Yeah, yeah,
published.
yeah. Definitely, definitely.
Yeah, because very
Okay.
similar.
Ha, ha, ha.
Okay, thank you.
Okay, okay. Thank you.
So if there is no more question, then we can move ahead.
Yes. So
So our next speaker supposed to Dr. Arnab Chakrabarti, but due to some network issue, he is unable to give the talk. So we have planned that Dr. Shruti Agarwal will give the talk now. So let me formally introduce Shruti Agarwal. Shruti Agarwal is a PhD student from Delhi Technological University, and the title of her today's talk is Entanglement Detection in Arbitrary Dimensional Bipartite Quantum Systems through Partial Realigned Moments. So the Shruti, the stage is yours. So you can start now.
Okay, good morning, everyone. So thank you for the introduction. Let me just share my screen. Am I audible?
Yes, you are audible.